Yo, welcome to NucleoGenesis project. My name is Dr. James Utley. I am your resident codebreaker data scraper, and we are here at part 7. So the NucleoGenesis project, if you don't know, is a temporal framework for eukaryotic nuclear blueprint archival and reconstruction, which is a mouthful. It means that we're building a nuclear blueprint manifest that can be used in the future. It uses two fractions, a fresh biological fraction, as well as an archival fraction, which is the fresh is test right now. The archival is embedded in a dried blood spot card. So, all right, so now is part 7, as I mentioned. Let's get into it. That is right here, which is section 2.5, dried blood spot molecular preservation kinetics. Dried blood spots preserve nuclear information through a fundamentally different way than cryostorage or solution-based storage. Once deposited and desiccated, DBS samples transition into a low water activity solid state system in which molecular degradation is governed primarily by residual moisture, temperature, and intrinsic chemical bond stability. So in this regimen, degradation kinetics are slow, predictable, and amendable to quantitative modeling, ensuring long horizon forecasts of genomic and epigenomic recoverability. So because it's in a dry blood spot, it's meant to be preserved, and so it's limited by the amount of moisture that's being introduced to the card. Right? Okay, so DNA fragmentation model. So this is the math that governs the degradation over time, and that is a DNA fragmentation in a dry blood spot is dominated by spontaneous hydrolytic cleavage of the phosphodiester backbone, right? So breaking the DNA under a dried out condition. This process proceeds a first order kinetics, which with respect to fragment length, reflecting a memoryless bond breakage process distributed along the polymer chain. The temporal evolution of this means that the DNA fragment length is therefore modeled as by here in this equation. This formulation captures the empirical observation that longer fragments possess proportionally more susceptible cleavage sites, while shorter fragments exhibit a correspondingly lower absolute breakage probability. So the effective rate constant K is a composite term reflecting both thermal activation and moisture mediated breakdown, which is right here, where the K0 is a pre-exponential factor incorporating molecular collision frequency. This variable is an active energy, right? So the E is for energy, for hydrolytic cleavage. R is the universal gas constant that is always, and T is the absolute temperature. And so you see how this framework is made up. Right? So empirical and theoretical studies of DNA backbone hydrolysis place the activation energy, or the EA, in the range of kilojoules per milliliter, right here, kilojoules per mole, consistent with the reaction that is strongly suppressed at ambient temperatures in the absence of liquid water. However, residual moisture dramatically accelerates cleavage by facilitating proton transfer and nucleophilic attack. This effect is captured by the humidity-dependent modulation, which is here. Right, so relative humidity is RH right here. And this sublinear dependency below 30% relative humidity reflects a diffusion limited regimen in which water molecules are sparsely distributed within the cellulose matrix of the dry blood spot card. Okay, we're moving on to the next page, right? And again, it's going to observe a capillary condensation, microhydration layers, and how they form. So basically it's all about moisture. So it's like you dry it out in the dry blood spot, and then the residual moisture from humidity, etc., is what you're kind of controlling for. All right, so the L0 denotes the initial post-deposit fragment length and distribution, typically centered around 40 to 60 kilobytes for leukocyte-derived DNA, or kilobases, sorry. This model predicts preservation of mean fragment length in the order of 10 to 20 kilobases after about 30 years, sufficient for long read scaffolding. Linked read reconstruction, the high confidence haplotype phasing when combined with modern assembly algorithms. And that is this, right? So it's a real basic type formula. Basically, it's looking at 40 to 60 kilobases, and then after the time, and the kilobases is reduced, of course, because of degradation over time. And then now it wants to talk about the methylation stability. So DNA methylation exhibits markedly greater stability than the phosphodiester backbone due to its encoding in covalent carbon-carbon bonds, right? The primary degradation pathway under 5MC under dry conditions is spontaneously a process that is both chemically rare and kinetically suppressed in the absence of water. All right, and this gets really kind of complicated in the chemistry of it, right? But what we're doing is we're trying to look at some stability factors, which is the leukocyte DNA, and then the methylation stability. Now we will get this last part, which is the genomic content recoverable from dried blood cells is not uniform across blood cells, right? And you can see that it has a breakdown here, like the leukocyte contributions to the DBS genomic pool, which is what's been inoculated in the dried blood spot, right? So that's the leukocytes, monocytes, neutrophil, and basophils. And what we're trying to look at is the quality of the DNA. So we're looking at the T lymphocytes. It looks like the DNA quality is high, but it has no low nuclease content, long fragments, whole genome sequencing, haplotyping, and then the monocytes is also high, right? So you can see this is a breakdown here. Leukocytes and monocytes contribute disproportionately to long fragment DNA recovery due to their relatively low endogenous nuclease activity and more stable nuclear architecture. And so, like when I first began this project, I was only looking at a lymphocyte nucleus, right, that had been kind of mummified in the dried blood spot card. But we have since kind of zoomed out and allowed and just kind of look at other cells, right? So taken together, these effects imply that the dried blood spot derived genomic data represents a composite signal arising from multiple degradation regimens. Modern reconstruction workflows can exploit this heterogeneity by weighing long fragment information from lymphoid cells against high depth short fragments from granulocytes. So it's kind of like taking everything to build this like nuclear blueprint manifest for a synthetic nucleus. Further reinforcing the viability of dried blood cells as a long-term genomic archive, right? Because we're looking at the fraction. So we got the cell type, we're looking at the fraction, we're looking at the DNA quality that we know from the research, and then the analytical utility, right? Okay, and that brings us to 2.6, which we're going to stop for today. So again, if you want to read this whole paper, right, it's at syndicate-labs.io under the NucleoGenesis project. My name is Dr. James Utley, and I'll see you in the future. Peace.